Greetings, ladies and gentlemen. I welcome you all to our today's lecture. So basically last time we talked about sequences where we looked at different definitions, and majorly we talked about what a bounded sequence is. So we shall extend the same knowledge and look at this theorem. The theorem says a sequence AN is bounded if and only if there exists a positive real number m such that magnitude of an is less or equal to m for all values of n that we pick from the set of natural numbers. Let us try to recall some few things. Last time we talked about a bounded sequence, where basically we said a sequence is said to be bounded if one, it is bounded above, and it is also bounded below. It must satisfy these two conditions. The sequence is bounded if it is bounded above and bounded below. And for that case, we came up with the conclusion that if a sequence AN is bounded, then it must be lying within two real numbers, such that we have, for example, k less or equal to each of the terms of the sequence less or equal to this k here. So where our k was less or equal to this. So these are different real numbers, k and k, for which this k, this one here, this k is less or equal to this one here. So basically we said a sequence is bounded if it satisfies this condition. In other words, if the terms of the sequence lie within two real numbers. So that is basically what we say. So we want now to prove this theorem. We shall be proving theorem using two parts, the necessary part and the sufficient part. One, we shall first of all assume that this sequence AN is bounded, and if it is bounded, then we must get, or we must show that this one is true. Again, because this is if and only if question. So again, we must also show that if there exists a positive real number such that this is true, then we must also show that the sequence AN is bounded. So we shall be basically dealing with two parts of this question. So let us look at the proof. So to look at the proof, let us begin with the necessary part. So the necessary part, as I said, we shall first of all assume that a sequence is bounded, then we show that this is true. So let our sequence AN be bounded. So let this sequence be bounded. And now we need to show this. So if the sequence is bounded, what happens? If the sequence is bounded, as we have seen, it means that there exists. It means that then there exists. It means there exists. It means if AN is bounded, then it means there exist two real numbers, for example, h and k, for which h is less than k, such that our terms of the sequence, because we are saying this sequence is bounded, we are taking an assumption that our sequence is bounded. And if it is bounded, as we have seen, then it means the terms of this sequence must be lying within two real numbers. So that's why we are saying then there exist two real numbers, h and k, for which h is less than k, such that the terms of the sequence, or the terms of the sequence, lie between these two real numbers. So that is from the definition. This is by the definition that for a sequence to be bounded. If a sequence is bounded, then this is true. Now, let us let m to be the maximum of these real numbers. So since these are real numbers, they can be positive or negative, but let m be the maximum of the magnitude, meaning we shall be considering the positive parts. So that is, m is the maximum of magnitude of h and magnitude of k. So if that is the case, then it implies that since m is the maximum of the magnitude of h and magnitude of k, then it means magnitude of h will be less or equal to m. Remember, m is the maximum of this. So it means magnitude of h will be less or equal to m, and at the same time, magnitude of k will be less or equal to m. By definition of this one and this, then we can write that if magnitude of h is less or equal to m, it means we can write negative m is less or equal to h, which is less or equal to m. We can write this by definition of a magnitude. Magnitude of x is same as, when you are considering magnitude of x less than, for example, 1, less or equal to 1, it means negative 1 is less or equal to x, which is less or equal to 1. So that is by definition, meaning that if I have a magnitude of h less or equal to m, it means I can write negative of m less or equal to h less or equal to m. And at the same time, I can as well write, for this case, this one here, I can also write negative m is less or equal to k, which is less or equal to m. I can write this by the definition of magnitude of a number. So I can write that. So let us have this one as equation number 2. So already we have got our equation 1, which is h is less or equal to an, which is less or equal to k for all values of n picked from this set of natural numbers, and we have this equation as well. Now from 1 and 2, from this one here, we can easily see that from this we have h is less or equal to an less or equal to k, but this is negative m. Let me start with this. We have negative m. This from here, negative m is less or equal to h, isn't it? Negative m is less or equal to h, but let us come back to this. But h is less or equal to an, but h is less or equal to an. So we are coming, negative m is less or equal to h, but h is less or equal to an. At the same time, an is less or equal to k. But when we look at this, k is also less or equal to m. We have this. We have negative m is less or equal to h. Negative m is less or equal to h. But this h is less or equal to an, which is less or equal to k. But this k, when you come back to this, is less or equal to m. So I can write this from equation 1 and 2. And if I write this, it means this is true for all n which is picked from the set of natural numbers. So having that, we have written that negative m is less or equal to h, which is less or equal to an, which is less or equal to k, which is less or equal to m, for all values of n picked from the set of natural numbers. So if that is the case, what does this one imply? Can we say that negative m is less or equal to an, which is less or equal to m? Because we can easily clearly see that from this we can easily write that. And this is true for all n picked from the set of natural numbers. So looking at this, remember, by definition of magnitude, we said if you have a magnitude of x less or equal to 1, this is same as negative 1 less or equal to x less or equal to 1. So if I have this, it means this is same as magnitude of an less or equal to m. And this is for all values of n picked from the set of natural numbers. Looking at this, this is what we needed to prove, because our statement says a sequence an is bounded if and only if there exists a positive real number m such that this is true. So we started with by rating that our sequence is bounded, and we have got this one here. So our sequence is bounded, and by definition of boundedness, we have clearly said there exists real numbers h and k, which will make this one true. So we by assuming this, we have obtained this. So the necessary part will be proved. So you started from here, you have got this. That is what we wanted. So the next, we shall start with this, then we see whether we shall be able to show that a sequence an is bounded. So that will be the first part of the proof, and that will be proved. So let us look at the second part. That is what we call the sufficient part now. Now, for the sufficient part, we shall begin with the converse. This is the converse part. Now, we are saying that a sequence, this is bounded. Remember, we started with this. We showed that this is true. And again, we are starting with this part. That is the converse part. There exists a positive real number m such that this is true. So we are starting with by rating that there exists a positive real number m such that this is true. So we want to show that a sequence an is bounded. Now, from this, we are saying let m be a positive real number such that this is true. Now, what does this one mean? If you have magnitude of an less or equal to m, this one implies that negative m, by definition of magnitude of an, is less or equal to an, which is less or equal to m, by definition of the magnitude of a number. So we can write this, and this must be true for all values of n picked from the set of natural numbers. But when you look at this, what does this one imply? When you look at terms of the sequence being between two real numbers, because this is a real number, this is a real number. So that one implies clearly, from this, we can clearly say that the terms of this sequence are actually bounded between two real numbers. And if this is the case, then clearly we can easily say that an, the sequence an, is actually bounded. This is actually bounded. So from here, we can easily have this one proved. So this is also proved. So we have proved all the two parts, and that will be the required proof. Let us now talk about this note here. Clearly, we have proved the theorem above, and it is very important that you need to commit this to memory. You need to be knowing this, because it helps in defining what we call a bounded sequence. So let us talk about least upper bound and greatest lower bound of a sequence. We shall begin with the least upper bound of a sequence. We shall be saying if a sequence an is bounded above, as we had previously seen in our last lecture, we talked about a sequence being bounded above. So if you have a sequence which is bounded above, then it means there exists a real number, for example k1, such that your terms of the sequence are actually less or equal to k1. So, and that must apply for all the terms. All the terms, for you to say that k1 is the upper bound, then k1 must be greater or equal to the terms within the sequence under consideration. So, if you have a sequence which is bounded above, that real number, such that an, or the terms of the sequence are less or equal to that number is what we call the upper bound. So that is an upper bound of the sequence. Now let us look at a given example. For example, we looked at a sequence an for which the terms of the sequence are defined by 1 over n. We looked at such a sequence having terms like 1, a half, 1 over 3, 1 over 4, 1 over 5, and so on. We said that this sequence here is bounded above and is bounded above by number 1. So this one here. So meaning that we call 1 as an upper bound because all these other terms within this sequence are actually less or equal to 1. It means 1 is the value or the largest value within this sequence. So for that case, 1 becomes the upper bound. Now let us look at the case. What if you have another number? We have seen that 1 is the upper bound. If 1 is the upper bound, then what if you have a number like a 2? Because 2 is greater than 1. 2 is greater than 1. You can have a number like 3. 3 is greater than 1. So if you have a number like 2, like 3, like 4, like 5, or any other number that we can pick from the set of natural numbers, it can be 6, or any number which is greater than 1. It means for any number that is greater than 1, then it means all these terms of this sequence will actually be less than that number. Because if 1 is the largest number, then it means when you consider 2, 2 will also be greater than all the numbers within this sequence. 3 will be greater than all the numbers within this sequence. So we are saying if, for example, you have a number like 2 which is greater than 1, then it means all the terms of that sequence will actually be less than what? Less than that number 2. Because if all the terms are less than the number 1, if all the terms are less than this, and 2 is also greater than 1, then it means automatically all the terms will be greater than 2. All the terms will be less than 2. All the terms can be less than 3. All the terms can be less than 4. Because 4, 2, and 3 are already greater than 1. And all the terms here we have seen are less or equal to 1. So when we have such a scenario, then we shall also be saying that this 2 is also an upper bound. We have seen 1 is an upper bound, but 2 will also be an upper bound. Similarly, 3 can also be an upper bound. 4 can also be an upper bound because all the terms within this sequence will be less than the term that we shall be considering. If you consider 2, 1, 3, 4. So in other words, all the terms or all the numbers that are greater than 1, that is any number which is greater than 1, we are taking 1 to be our upper bound. But for our case now, we are using K1 to generalize. So if K1 is your upper bound, all the numbers that are greater than K1 will be called upper bounds. So as we have seen here, 2, 3, 4, 5, 6, 7, all those numbers will be called upper bounds. So for that case, it means if a sequence is bounded above, then it has got infinitely many upper bounds. Because if 2 can be an upper bound, 3 can be an upper bound, 4, 5, 6, 7, and so on. There are many numbers that are greater than 1. So all those will be upper bounds. So we shall be saying that a sequence that is bounded above has got infinitely many upper bounds. Now, as we have seen that we have got infinitely many upper bounds, then if we need to talk about the least upper bound, out of the upper bounds that we have seen, we saw that 1 is an upper bound, 2 is an upper bound, 3 is an upper bound, 4 is an upper bound, and so on. There are infinitely many of them. So which one is the least out of these? Remember, we are considering the sequence 1, 1 over 2, 1 over 3, and so on. So out of these upper bounds, which is the least upper bound? So the least upper bound, when you look at 1, 2, 3, 4, the least upper bound is actually 1. So this one will satisfy some properties. So in other words, we shall be able to say that of all the upper bounds of the sequence, if k is the least, then k is called the least upper bound. Out of the upper bounds that we have seen, the least upper bound is actually what we shall be talking as the least upper bound of that given sequence, and it should be able to satisfy these properties. Here, the property number 1 is that it should be, first of all, an upper bound, that we are talking about a 1 being the least upper bound. Or for that case, if we generalize and say k, for k to be a least upper bound 1, it must be upper bound. Clearly, these are our upper bounds. These are our upper bounds. So the first thing, since they are already an upper bounds, then we can select which one is the least. So there are two properties which must be satisfied. The first one, it is the upper bound of the sequence. It must be the upper bound for it to qualify to be the least upper bound. Then again, if you have any positive number, for example, epsilon greater than 0, when you get that upper bound, you subtract, for example, some given positive number, then it should be less than k. We are saying when you have, for example, 1, which is our upper bound, if you subtract a number which is like 0.05, you will get the number like 0.95. So when you talk about 0.95, then we can clearly see that 0.95 is less than 1. So that's why we are saying for a given epsilon greater than 0, k minus epsilon is less than k. This is true. So if this is true, now, since k is the least upper bound, we are saying k is the least upper bound, then it means k minus epsilon is not even an upper bound, which means that there will be some of the sequences, there will be some of the terms, within this sequence that will be greater than, k minus epsilon. In other words, when we talk about 0.95, so when you are considering 0.95, there will be some terms that might be greater than 0.95. Now, having looked at the least upper bound, let us also talk about the greatest lower bound of the sequence. Now, last time we also talked about a sequence being bounded below. And we used also an example of the same sequence, that is 1, a half, a third, 1 over 4, and so on. Okay, we used this. And we said that as the terms keep on increasing, then our terms will be coming towards a 0, because you will have 1 over 2, 1 over 3, 1 over 4, 1 over 100, you have 1 over 1,000, you have 1 over 10,000, you have all these terms here. So as the terms as n keeps on increasing, it means the terms will be coming approximately to 0, because if you have 1 over, for example, 1 million, that term will be 0.0000001, something like that. So it is coming towards 0. So we said that 0 for that case is our least, is actually our lower bound, because 0 will be the smallest number, for which all these other terms will be greater or equal to 0, because all these other terms here, that any term that you will consider 1 out of 1 million, that term will be greater or equal to 0. It will be approximately coming to 0, but they are also, all these other terms will be greater than 0. So that is why we said 0 will be a lower bound, or is the smallest number for which all these other terms within this sequence are actually greater or equal to 0. So for our case, we are having 0 as our lower bound. So what we shall be saying is, if a sequence is bounded below, then there exists a real number, for example k1, such that the terms of the sequence are actually greater than that real number k1. So we are saying an, or the terms of this sequence, are greater than that real number, and this is applicable for all the terms, meaning for all n that you pick, then a1, a2, a3, a4, all those terms there will be greater or equal to k1. And that's why when we used such an example, we said that k1 can be 0, since all these terms here will be greater or equal to 0. Now let us look at the case. What if you have a number like -1? Because we are saying all these terms 0 will be, all these terms will be greater or equal to 0. But when you look at a number like -1, -2, for example, -3, such numbers here, when you look at such numbers, when you look at these terms here, it means these terms will be also greater or equal to -1, will be greater or equal to -2, will be greater or equal to -3. So if you have a case where, for example, k2 is less than k1, if you have, for example, k2 less than k1, so your k1 is the lower bound. But if k2 is also less than k1, it means k2 will also be a lower bound. K3, if k3 is also less than k1, and your k1 is the lower bound, is the smallest number, but you are finding other number which is smaller than that, so it means k3 will also be the lower bound. So if 0 is the lower bound, but there are other terms, for example, that are less than 0, it means all the sequences, for example an, will be greater or equal to all those terms that will be less than 0. So how do we call such terms there? So we shall thus be saying that any number that is less than k1, remember k1 is our lower bound, so any number that will be less than k1 will actually be also a lower bound of that given sequence. Now to talk about the number of lower bounds, because there will be many numbers that will be less than that k1. So if we have very many other numbers that are less than k1, it means we shall be having infinitely many lower bounds. So there will be infinitely many lower bounds, because if you have k1, obviously there will be some other numbers that will be less than k1, and all those will qualify to be called lower bounds. So we shall have infinitely many lower bounds, and for that case, that is for a sequence which is bounded below, we'll always have infinitely many lower bounds. So let us say, out of these lower bounds, what is the biggest one? What is the biggest lower bound. That is what we need to talk about. So the biggest will give us what we call the greatest lower bound. So we have, for example, used our example where we had our sequence 1, a half, a third, or going, and we are saying that all these terms, as n keeps on increasing, they will be coming closer to 0. And we are saying that our 0 will be the term for which all these other terms n is greater or equal to 0, because all these terms, when you consider 1, a half, a third, will be greater or equal to 0. When you consider 1 out of 1 million, it will be approximately equal to 0, but it will be greater than 0. So all these terms here will be greater or equal to 0, all the terms that you consider here. So for that case, 0 becomes a lower bound. But we are also saying there are very many other real numbers. For example, -1, -2, -3, -4, -5, -5.5, -1.5. There are very many other numbers or real numbers that are actually less than 0. So when you consider all these terms here, we realize that actually all these terms will be greater or equal to -1, will be greater or equal to -2, will be greater or equal to -3, and so on. And for that case, that's why we said there are infinitely many lower bounds. But out of the 0, out of the -1, out of the -0.5, out of -5.5, out of -4, all those terms that are less than 0, which is the greatest? So when you look at all these, the greatest is actually what? Is actually 0. So 0 becomes the greatest lower bound. And the greatest lower bound will be able to satisfy some few properties. One, if one of them, it should be, if we say k is the greatest lower bound, first of all, k must be a lower bound. If you say 0 is the greatest lower bound, if 0 is the greatest lower bound, then this 0 must first of all be a lower bound. And the next one, if you have any positive number, epsilon, then when you get k plus epsilon, it will always be greater than k, which is surely true. But k plus 3 will not be even a lower bound. Why? Because we are considering this to be the greatest lower bound. First of all, it means when I add there a number like, for example, 0.05, it means I will get 0.05. So the 0.05 surely cannot be the greatest, cannot be a lower bound, because there will be some terms, there will be some terms out of this sequence that will actually be be satisfying this condition. That when you get that term that you will pick out of this sequence will actually be greater than, will actually be less than 0.05 that you have used. So there will be some terms out of this sequence that will be less than 0.05. But remember, for the lower bound, then 0.05 should be 0.05 should be less or equal to all the terms. But because you have added there, then this one will not be true, because you will have some terms which will not satisfy this given condition out of other terms that you are considering. So that's why we are saying if k is the greatest lower bound, then for any number that you add, there will exist some epsilon that you will add on this one, such that this condition does not satisfy. And for that case, if that one happens, then truly k will be the greatest lower bound. Let us now briefly talk about limit of a sequence. So to talk about limit of a sequence, we are simply referring to the value that the terms of the sequence, the value that the terms of a sequence approach to, as the sequence progresses indefinitely, So what we are talking about is that as the terms of the sequence keeps on progressing, it can be either increasing or decreasing depending on the nature. So as the terms of the sequence keeps on progressing indefinitely, then the value to which those terms are tending to is what we shall be calling a limit of a sequence. So we can easily define the limit of a sequence as, for example, let us consider our sequence an, and let us have L as any number picked from the set of real numbers. So when will L be said to be a limit of a sequence? L will be a limit of a sequence. For this case, that is the value we are talking about. So L will be, if L is that value for which the terms of the sequence approach as the sequence progresses indefinitely, we shall call L as the limit of a sequence. Now we are saying an is our sequence, L is any number picked from the set of real numbers. So we shall be able to say that L is the limit of a sequence an if you have epsilon greater than 0. Epsilon is any positive number. And also you have a number if there exists, for example, m that we pick from the set of natural numbers, such that you are able to write that when you get an, that is the term, nth term, then you subtract L, which you are saying is your limit, then this absolute value should be less than epsilon, meaning that the absolute value of the nth term minus L, its magnitude should be less than the chosen epsilon value. Or else you can say L is the limit of the sequence an if you can be able to write that an is tending to L. So we shall be able to say L is the limit of an if the nth term, that is an, is tending to L as n is tending to infinity. Or else you can say if you take the limit as n tends to infinity of an, then what you get will be L. So the limit of an for which n is becoming larger, then if is giving you L, then your L becomes your limit of that given sequence. And we are saying the definition of the limit of a sequence asserts that for any given epsilon, that is for any positive number, however small it may be, all the terms of the sequence except m minus 1 terms. Remember, for this case, we are considering our terms starting from, we are taking the terms for which we are having m picked from the set of natural numbers. So for all other terms before m, that is m minus 1 terms, will actually be scattered anywhere but will not lie within this given range, that is of L minus epsilon and L plus epsilon. The terms that lie within this are for the terms that satisfy this given expression for which you are taking n greater or equal to m. So it means m minus 1 terms will not lie within this given range here. So for that case, if we need to know how this one comes. Basically, it comes from the definition. If you have magnitude of an minus L, which is less than epsilon, it means you can easily say by definition of absolute value of a number that it means negative epsilon is less an minus L. an minus L, which is less than epsilon. So when you take L this side, it becomes L minus epsilon is less an, which is less L plus epsilon. So which means that L, or the terms that will be satisfying this given range of L minus epsilon and L plus epsilon, will be for all the values of, for all n greater or equal to m. So that will be the definition of the limit of a sequence. To understand better about the limit of a sequence, we can take some few examples. If, for example, you have a sequence an, for which the terms of the sequence are defined by 1 over n. We have been looking at this sequence for some time. Now, if you take the limit, we want to know the limit of this. If you take the limit as n is tending to infinity, or as n is increasing, of an, it means this will be same as taking the limit as n tending to infinity of 1 divided by n. So 1 divided by n, we are saying n is becoming extremely large. So where will this sequence be tending to? So because we understand that when you get 1 divided by a very big number, this one here will be giving you 0. Because 1 divided by, for example, 10 millions, it means the value will be 0.000000001, something like that. So you realize that your limit, or the 1 divided by a very big number, or as n increases, then this one will be able to give you a 0. But now, if you arrange this normally, if you have your sequence, you put, for example, n equaling to 1, you get 1, n equaling to 2, you get a half, you get a third, you get 1 over 4. We have been looking at this, you get 1 over maybe 100, get 1 over 10,000. So as n is increasing, so you realize as all these terms here, or as n, or as the terms of this sequence keeps on progressing indefinitely, all these terms will be coming towards what? Will be coming towards 0. So it means an will be tending to 0 when n is becoming extremely big, because the last value will be 0, because all others will be 0.00 something like that. So you realize that the terms of the sequence will be tending to what? Will be tending to 0. So for that case, we call 0 as the limit of the sequence. So 0 is said to be as the limit of the sequence. Is the limit of the sequence. So that is how we can easily tell the limit of the sequence. But if you have, for example, your sequence for which the terms, for example, an is n. So it means as n is 1, if n is 1, it means this will be 1. This is a1. So a2 will be 2. a3 will be 3. a4 will be 4. So it keeps on. It means a100 will be 100. Next will be, for example, 1000. So it keeps on increasing. So let us look at the case. Where will an be tending to as n is becoming very big? If n is becoming very big, it means an will also be becoming, all the terms will keep on increasing. Will keep on increasing, because you can see the terms keep on increasing. We cannot tell that maybe it will stop at one, maybe 10,000 or 10 millions. It cannot stop there, because there will be 20 millions, something like that. So an will be becoming extremely large. All the terms will be larger as n is tending to infinity. So you realize that actually when we come to convergent and the divergent sequences, you realize that your sequence is divergent because it has no limit. So we shall be coming to that. So you realize here that your limit when n is tending to infinity, when this is your n, then this will still be infinity, because when n is becoming big, whatever value you have will be the same output here. So that is basically what we shall have. So you realize that such a sequence or an does not approach any finite value as n becomes extremely big. So clearly this sequence has no limit. So hence the sequence has no limit. There is no value for which the terms of the sequence will be approaching to when n is becoming big. Has no limit. So that is basically some few examples, but we shall come to more examples when we go on. Let us talk about a convergent sequence. So a convergent sequence is simply a sequence. This is simply a sequence whose terms, so if you have a sequence whose terms approach a specific value, they approach a specific value. Which value, if you recall, we called this value as a limit, as the number of terms keeps on increasing. So if you have such a sequence whose terms approach a specific value or approaches the limit as the number of terms are increasing, then we shall be saying that such a sequence is a convergent sequence. So we shall be saying a convergent sequence is simply that sequence whose terms approach a specific value as the number of terms keeps on progressing to infinity. So in other words, if you take the limit as n is tending to infinity of an, then and this one gives you L, then we say that actually this sequence an converges. This sequence converges to L. So this sequence converges to L, and for that case, it means it is a convergent sequence. So if the limit of an as n is tending to infinity exists and is L, then we shall be saying that the sequence is a convergent sequence. Let us now talk about the theorem. It says that every convergent sequence has a unique limit. In other words, a sequence cannot converge to more than one limit. So it means if a sequence is convergent, then it must have only one limit. So it is very important that before we prove the theorem, we still recall the definition of a convergent sequence. A sequence is said to be convergent if an minus L is absolute value of an minus L is less than epsilon. Remember, epsilon is a positive number or a positive real number, and this one here must be true for all n greater or equal to m. Remember, our m is a positive integer that depends on epsilon. So if this condition is satisfied, then we say L is the limit. And if the limit exists, then that sequence, it means it will be convergent. So we also looked at if you take the limit of n tending to infinity and you get of an and you get L, which means that L is the limit, then we shall be saying this sequence is converging to 0. So that is briefly what we talked about when we are dealing with convergent sequence. Now, let us look at the proof. We want to prove that every convergent sequence has a unique limit. We shall prove this by a method of contradiction. We shall prove this by a method of contradiction. So let us look at the proof. We shall say, let if possible, the sequence which is an, let if possible the sequence an converge to two distinct, let if possible our sequence converge to two distinct real numbers, say L and L dash. These are two distinct real numbers. Remember, we are proving this by a method of contradiction. Remember, what we are interested in proving is to show that there exists a unique limit, or the limit is only one. The limit is only one. But for us, we are saying, let us prove this by contradiction. What if we say this sequence is converging to two limits which are different? What does that one? So this must bring us to a given contradiction. So let us have this. Now we shall let, for example, our epsilon to be equal to the absolute value of L minus L dash, absolute value of this. So what does this one imply? We are saying let epsilon, and remember from the definition, the epsilon that you consider must be greater than 0. So let us see, if we let epsilon to be equal to this, does this one mean this expression is greater than 0? Let us look at that. So we are saying that absolute value of L minus L prime, we need to see whether it is greater than 0 for this to hold for a convergent sequence. You know, by definition, the epsilon must be greater than 0. So we are saying let epsilon be equal to this, but we need to show that this expression is actually greater than 0. So for that case, let us say, since L is not equal to L prime, because these are distinct real numbers, which means they are not equal. So can we say that magnitude of L minus L prime will be actually greater than 0, so that epsilon is greater than 0? Can we do that? Because we can easily do this, because we are saying L is not equal to L dash. If the two are not equal, it means L minus L dash is actually not equal to 0. And if that is true, it means L minus L dash can be a positive value or it can be a minus value. But if we say we take the absolute value, it means L minus L prime will actually not be equal to 0. It will be greater than 0, because first of all, this is not equal to 0. So the absolute value must be greater than 0. So that's why we can write this. So if that is the case, we already have epsilon greater than 0. Now, let us have the sequence. Now, if the sequence an, now if the sequence an converges to L, what happens? Converges to L. What happens? It means that by definition, for a given epsilon, as we have seen, for a given epsilon greater than 0, it it means there will exist some positive integer. There exists a positive integer, which positive integer we can call m1. And remember, this m1 depends on epsilon, such that that is by definition such that an that is absolute value of an minus L. We are saying an converges to L, which means by definition this will be less than epsilon. So, but let us have this as epsilon by 2. And this must happen for all n greater or equal to m1. So that is for the sequence, if this sequence converges to this, because we are saying the sequence is converging to two distinct real numbers. So what if this sequence is converging to this? What happens is converging to L. It means this one must be true. Now also the sequence converges to L prime, because we said that let our sequence converge to two distinct real numbers, L and L prime. So for the sequence converging to L, by definition we shall get this. And also if the sequence converges to L dash, that is our sequence, if the sequence an converges to L dash, it also implies that for given epsilon, given epsilon greater than 0, there exists a positive integer, say m2, such that when you get an minus L prime, this will be less than epsilon over 2. This will be less than epsilon over 2, and this happens for all n are greater or equal to m2. So that is what we get by definition. Now let m represent the maximum value of m1 and m2. m1 and m2 are two positive real numbers. So if we let m to be the maximum of the two, it will imply that we shall be having magnitude of an minus L. We shall be having this expression here. This expression here will be occurring for every value of n greater or equal to m, and this one here will occur for every n greater or equal to m. So this will be, and then magnitude of an minus L will be less than epsilon over 2, and this happens for every n greater or equal to m, because we are saying m is the maximum of m1 and m2, and the same applies, that is an minus L prime will be less than epsilon over 2 also for n greater or equal to m. So clearly, let us have this one here as equation number 1. So now we shall also say, now let us consider L minus L prime. We shall need to apply the triangle inequality, but before that let us first introduce in an. So if we have magnitude of L minus L prime, I can say this is L magnitude of L minus an plus an, and then this is a 0. You are creating a 0 using an, that is minus an plus an. Of course it will give you 0, but without changing meaning. So here we shall have negative L prime. So clearly this is still the same as having an L minus, this is minus of an minus L. If I put out to the minus, then plus, this is same as an minus L prime. So I can rewrite this very well. This is minus of an minus L plus an minus L prime into magnitude. So clearly these two are the same, but I will introduce in what we call the triangle inequality. For triangle inequality, if I want to introduce in triangle inequality, this will be less or equal to absolute value of this, that is an minus L, then plus magnitude of an minus L prime. That is when you take or when you use what we call the triangle inequality. So triangle inequality, if you have magnitude of x plus y, by triangle inequality this is less or equal to magnitude of x plus magnitude of y. So we shall do the same. We shall use the triangle inequality to get this expression. But we understand we already have an minus L as this here, this one here, and we already have this as that. So from equation number 1, we can say that this expression is less than epsilon over 2. This is less than epsilon over 2 plus this one here is also less than epsilon over 2. So the overall sign here will be a less than sign. So clearly we shall be able to obtain this as epsilon. Now from there we shall have magnitude of L minus L prime less than epsilon. So this is the expression we shall obtain. Now from here, let us come back to our expression. So we had let, if possible, this one to converge to two distinct real numbers, L and L prime, and we had let our epsilon to be magnitude of L minus L prime, meaning that if I have this, I will equate it, or I will substitute it with epsilon. Now I have got my expression as this, and we are saying this by what our assumption was. This is epsilon. So clearly we have epsilon is less than epsilon, which is wrong. This is very wrong, because you cannot have a 2 less than 2. 2 cannot be less than 2. 2 is equal to 2. So 2 cannot be less than 2, which is not true. So this will lead us to what we call the contradiction. So you realize the essence of creating this one here was basically to come up with the contradiction. Remember, we are proving this with the contradiction. So we wanted to see if magnitude of L minus L prime will be satisfying this expression. So that's why we had to introduce in the magnitude of L minus L prime to see whether it will give us epsilon. So from here we were able to create a 0, and that 0 is created by introducing an, because when you look at what we have an minus L, we have an minus L prime. So we must look for the ways of introducing in an, and we introduce in an by creating a 0, which 0 will help us to create this expression and this one here. So basically that is what we have done. So looking at what we have here, still when you open the brackets, you will be able to come up with the same expression. So having substituted for epsilon over 2, we get epsilon. Clearly, we get this expression less than epsilon. But this one here, initially we were given that, or we had let that L minus L prime be equal to what? Be equal to epsilon, meaning that epsilon is less than epsilon, which is not true. And if that is not true, it contradicts, because this statement here contradicts. So star contradicts, the equation star contradicts, this is equation star contradicts the assumption, contradicts the assumption, it contradicts the assumption that that epsilon is equal to magnitude of L minus L prime. And that contradiction is brought about by this, because epsilon cannot be less than epsilon. And if this is true, then that one implies, then this clearly implies that our assumption, this clearly implies that our assumption is wrong. Our assumption is wrong, but our assumption was L is not equal to L prime. So our assumption, which is this, is wrong. Thus, L must be equal to L prime. And if L is equal to L prime, clearly you will have shown that a sequence cannot converge to more than one limit. And for that case, we shall have our theorem proved.
Yeah.